So, good afternoon. Welcome to the second session on electromagnetics. The agenda was to revise on vector calculus. So, last time we discussed a bit on uh, vector calculus. We finished vector calculus. We did a review of Faraday's law. We are yet to do the Lenz's law. The rest of this is going to follow in today's class. So, last time what we saw was some basic concepts. I talked to you about what is a scalar field and a vector field. He said temperature is a scalar field, velocity of water on the surface of a river is a vector field, and so on. And once you have vector field, we wanted to define what is line integral, surface integral. Line integral tells you the effect of a vector on the line that we are considering. Of course, if that line is a continuous or it's a loop, then you call it as a loop integral. We talk about surface integral. Surface integral represents the flux of the vector field, effect of how much vector field is crossing the surface. And again, as if that surface is a closed surface, we say it's a closed surface integral. So that was about integration. And about differentiation, we discussed gradient, we talked about divergence, we also talked about the curl. Now, we established two important theorems. One is a Stokes theorem and the other one is a Gauss divergence theorem, where we connect the divergence of a vector to the surface integral using divergence theorem and curl of a vector to the line integral, loop integral through the Stokes theorem. Now, once we do that, we are now ready to learn the rules of electromagnetics. We started with Faraday's law. Faraday's law gets coupled with Lenz's law, and law says that any time varying magnetic field produces an electric current. So, you are talking about the source of electric current. Source of electric current is a time varying magnetic field. So, and the way the electric current is quantified as to how much magnetic field, how much electric current is produced is decided by how fast is the flux changing, magnetic flux changing. So, surface integral B dot ds is representing the magnetic flux. Rate of change of that is represented by this d by dt, and this negative sign comes about because of Lenz's law. Okay. So, the flux is B dot ds, and we were trying to work out an example as to the case. If you recall, we had a loop whose length is b, whose width is a. It is kept in a magnetic field. The peculiarity of this magnetic field is that it is oscillating sinusoidally. It is represented as B equal to B naught cos omega t, and it is in the y direction. Y is into the plane of the board. So, this is my y direction here, and the loop is the blue colored loop that is kept in that oscillating magnetic field. Now, we want to find out, because of the fact that the field is oscillating, the field is moving up and down, its strength is changing as a function of time, what is the EMF induced, how much current is induced in the coil. So, we were planning to apply Faraday's law, which says that line integral. So, the Faraday's law statement is that line integral E dot dl, closed loop integral E dot dl is d by dt of the magnetic flux, and so the magnetic flux is what we try to calculate. So, magnetic flux is surface integral B dot ds, and we have to be careful in calculating this surface integral. We want to be finding out where is the surface normal. So, the simple rule to connect between surface normal and the loop integral is that when I use my right hand to trace the loop, so my loop that I considered is in the clockwise direction. So, when I move my fingers of the right hand to trace the direction of the loop, the direction of the thumb follows the direction of surface normal, right. So, the direction of surface normal is into the plane of the board. That is what we realized yesterday, and then we go ahead and perform this integration. We got the flux as AB naught cos omega t, and I apply Faraday's law, and so I got surface integral loop integral E dot dl is equal to AB B naught omega sin omega t. Obviously, this is the induced EMF, and the direction of current because of this induced EMF is this way. If this is the loop, because I try to calculate this circulation, so the direction of current is shown there. Now, there is a very interesting understanding that we can make from this example. What we can think of is, what we calculated is, we started with a magnetic field V naught cos omega t ay. So, this is the cos, and the result is an induced EMF E dot dl, which is equal to AB B naught omega sin omega t. What is this meaning of this loop integral? This loop integral E dot dl is actually telling me the induced current, induced electric current in the coil. This is the source for the induced current. Depending on the resistance of the coil, I can now calculate the current. What is interesting to see is that this induced current, if you look at the right side of that expression, the induced current is dependent on omega, which means omega is the speed with which, the angular frequency with which the magnetic field is oscillating. So, larger omega means larger speed, which means that if the magnetic field is oscillating at a faster rate, then larger is my induced current, induced EMF, and hence the induced current. It is dependent of course on AB, which means if I take a large coil, I get more current than if I take a smaller coil. But the most interesting part is not either of these. The most interesting part is the fact that your current, the cos is varying as cos omega t, and the result is varying as sin omega t. Now, let us try to understand a little bit more on this part. So, what I am going to draw is, I am going to plot as a function of time, I am going to plot the cos and the effect. The cos being my magnetic field as a function of omega t for convenience, so that I can, it's easy for me to find the turning points. So, if I plot this quantity B naught cos omega t at omega t equal to 0, obviously it is at B naught, the largest value. At omega t equal to pi by 2, it is going to cross through 0. At omega t is equal to 2 pi, it is going to take the negative, at omega t equal to pi, it is going to pick the negative maximum. At 3 pi by 2, it is going to cross 0 again, and again at 2 pi, it is going to go. So, the cycle is going to follow something like, this is how my magnetic field is going to behave, which means as time progresses, as t increases, my magnetic field is reducing, becoming 0, going to the negative maximum. Negative maximum means instead of pointing into the board, it is going to point outside the board. It is going negative maximum, it is again going 0, and it is going to maximum, and this is going to continue. It is not that it is ending here, its cycle is going to continue. I am just picking one cycle. Now, you look at the effect, the result. The result is AB B naught omega sin omega t. So, again I am going to plot this result as a function of omega t. Now, and again I am going to plot this for omega t is pi by 2, omega t is pi. I know that at 3 pi by 2, I know the values of sin omega t at these turning points, and I know very well that when omega t is equal to 0, my current omega t is pi by 2, sin becomes a maximum. So, it is doing this function, it is behaving this way. I mean, there is nothing special here, I have just plotted a sine and a cosine variation, one below the other, but there is a bit of a physical understanding here, which actually illustrates something, some important law. You see, as your magnetic field is in the decreasing direction, your current is increasing, which means that through this loop in this direction, the current is increasing. Now, as the current is passing through this conductor, we know very well that current carrying conductor, by Ampere's law, current carrying conductor produces a magnetic field. And what is the direction of magnetic field? Again, I have to use my right hand side, I have to trace the path of the current, the direction of my thumb is the direction of magnetic field. which means that the magnetic field due to the current carrying conductor is into. So, now remember the magnetic field that I am plotting in green is the magnetic field produced because this coil is carrying a current. This is not the magnetic field which was the cause. The magnetic field which was the cause is also in this direction, but during this instant of time this magnetic field is reducing. The magnetic field in the direction, in the y direction is reducing. But while it is reducing, what is happening is while the process of reduction of magnetic field in this direction is happening, a current is induced and the induced current is producing a magnetic field which is increasing along AY, which means as the cause is trying to reduce, the effect is trying to increase. The cause of current is the magnetic field that is trying to reduce as it goes from 0 to pi by 2. The effect, which is the current, and because of that current there is a magnetic field that is trying to increase. So, this is exactly Lenz's law. Any change that the cause is bringing in, the result is such that it tries to oppose that change. Similarly, if you see this cycle here, for example, here for instance as the magnetic field is trying to increase, you will see that during this cycle the current magnetic field is going to a maximum here along y direction, the current is going to 0 along y direction, which means magnetic field is trying to increase, the current is reducing, which means reducing current means reducing magnetic field. If the cause is trying to increase, the result is such that it is trying to decrease. So, the induced EMF is induced in such a way that it tries to oppose the change. The change here is reduction in field, the induced EMF is trying to minimize the reduction. Here the change is increase in field in the negative direction, it goes maximum in this negative direction. The result is that my induced current is such that it produces a magnetic field which is opposing that change. So, this illustration actually tells us how this Lenz's law is working, right. So, that is one learning from this example. There is another learning one can have from this example, and the second learning is that, so in this example if you recollect, what we discussed was magnetic field in the y direction, all the magnetic field was in the y direction, and my loop was actually in the xz plane. This was xz plane and magnetic field was in the y direction. And we were trying to find out the flux. This is, let us say, this paper is the plane of the loop, magnetic field is pointing to you, pointing towards you. Now, when I calculated the flux, remember the flux is, so the magnetic field is here. So, the flux, so this is how I calculated the flux, right, B dot ds, and surface normal was this. But suppose the loop, because the loop is like this, the entire flux is through the loop. B dot ds, ds direction and the magnetic field direction were along the same direction. But suppose I had the loop, instead of this, my loop was like this. I keep the loop this way. Magnetic field is still pointing towards you. Loop is kept this way. This would mean that, what would be the flux in this case? What will be the direction of ds? You have to trace the boundary of the loop and I apply a right hand rule. Now, apply right hand rule, my surface is in this direction, right, which is my negative z direction in my picture. My magnetic field is in the y direction. Obviously, my B dot ds is at 90 degree with B and ds are at 90 degree with respect to each other. So, B dot ds is going to be 0. Okay. So, in fact, when I move the coil from this plane and as I keep moving the coil, it is only a component of B along the S, which is I am showing it as this is B along S, surface is turned now. B along S is what will give rise to magnetic flux. As you keep moving the coil, when the flux and the magnetic field are at 90 degree with respect to each other, my component is going to be 0. I will not get any induced EMF even though the magnetic field is time varying. Again, I turn, let us say I bring it back. When I turn and bring it back, again I get an induced EMF, which means that as I keep changing the orientation of the coil from this to, let us say, like this, right. So, as I change the orientation from your xz plane to, let us say, this was my, if this is my y and this is my x and this is my z, as I change the orientation from xz plane to xy plane, so here the induced EMF maximum, whereas here the induced EMF is 0, because B dot ds, because my B is in the y direction, my B dot ds is equal to surface integral B dot ds is equal to 0. Now, this simple concept, this simple fact that if the flux is not passing through the coil, if there is no, in high school you would have learned that if there is no flux cutting the coil, it actually means that the B dot ds is 0. If the flux is not cutting the coil, means the flux is in this direction, the coil is also in the same direction, there is no flux passing through the coil. If that is the case, induced EMF is 0. This very simple principle can be actually used, in fact people use it for finding the direction of an RF emitter or a transmitter. Let us say you are lost somewhere. Let us think about a sci-fi situation where you are lost in Mars. Okay, you have already gone to the Mars with so many satellites and you have lot of RF transmitters for your connectivity with the earth. Let us say you got lost and you want to know where the transmitter is, or even on the surface of the earth you are in an unknown place, you want to know where the transmitter, whether there is a transmitter, whether there is an RF transmitter and where is the transmitter. Another application I can think of is, let us say there is a enemy aircraft which is giving out some electromagnetic radiation for some aerial survey and you want to keep tracking the enemy aircraft, you want to know where that aircraft is. Okay, you are obviously not in a position to image it, take photograph, which is why you are using these kind of methods. So, the simple experiment you can do is, because it is RF, it will have electromagnetic radiation, and electromagnetic radiation we know very well that if this is the direction of propagation, if the radiation is propagating in this direction, it will have its electric field, let us say in this direction, and let us say magnetic field is in this direction. This is the direction of propagation. So, the idea is the following, I take a loop, okay, and so let us say my loop is this and I keep changing the orientation of the loop. I keep changing the orientation of the loop. I keep rotating the loop. If I keep the loop this way, or let us say I keep the loop this way, I get a large induced EMF in the loop. I am putting a galvanometer and finding out what is the induced EMF in the loop. I am putting a current meter and finding out what is the current in the loop. But let us say when I keep the loop in a specific direction, the induced EMF is 0. At all other directions, I get some induced EMF whose magnitude is changing as I am rotating the loop. But let us say at this specific, for example, let me draw this. Let us say I keep the orient loop like this, I am getting a magnetic, I am not getting an induced EMF. I am not getting an induced EMF would mean that can happen only if B and ds are perpendicular to each other. Now, that can happen only if the loop, the magnetic field is like this. So, because the magnetic field is like this, I can now say that the source is somewhere in this line, dotted line that I am drawing. But then that is not uniquely identifying where the source is. because that tells me only the line of sight, or it just tells me that the source can be anywhere here. Why did I locate that the source is anywhere along this line? Because perpendicular to that, if I keep my coil perpendicular to that line, I do not have an induced magnetic field. The only reason why I do not have induced magnetic field is because the magnetic field is parallel to the coil. So what I do next is I place this coil or a similar coil at a different vertical location, and let us say now I do the same experiment. I keep rotating the coil, and let us say now I find that when the coil is kept like this, I do not get induced EMF. All other positions of the coil, there is some component of B dot ds which is giving me induced EMF, but when I exactly keep like this, I get a null, which means that my magnetic field should have been like this. Only then I get a null. My magnetic field must have been like this. That is why I am getting a null. Now I draw a perpendicular line to that magnetic field, and I join these two lines. Point of intersection of these two lines, this is where my transmitter is. So this is a simple triangulation technique to find out the location of an unknown transmitter. This experiment you can do near your college, wherever you have your cell phone tower, you can do this experiment, because you can identify the location of the cell phone tower just by doing this simple Faraday's law classroom experiment. You would have definitely seen this classroom experiment where you have a coil, you have a magnet, the magnet is moving inside the coil, and you will see that whenever the magnet is moving inside the coil, the galvanometer is showing a deflection. That looks like a very silly high school experiment, but the same concept you can use for finding out the direction of a transmitter, position, location of a transmitter. All what you need to do is to take two coils, keep them at a height. You need this height so that you will know where you can extend and find out where the source is. You keep changing the location, direction of your transmitter. You can, and you're relying on minimum, because that's a unique direction in which the magnetic field and the coil are parallel to each other. At all other locations or all other orientations of the coil, you will have a component of magnetic field along the coil. So you are relying on the location of the position of the minimum. Obviously minimum also means that you should be able to get some induced EMF in other directions, right. So you repeat it for position 1 and position height 1 and height 2, extend this, and that is the location of your transmitter. So this is some so essentially it's a Faraday's law method of finding out the location of a RF transmitter using just two vertically spaced loops. Let us move on to another example to illustrate some hidden concepts in Faraday's law. One example 2. So the previous example we had psi is surface integral B dot ds, and this was you had a d psi by dt because B was a function of time. B was cos omega t, and so you had a d phi by dt. But it is not always necessary that B is a function of t. You could have ds changing as a function of time. Then also you will get an induced EMF. Because my line integral, closed loop integral E dot dl is actually d by dt of B dot ds. So even if I have a B constant, but ds changing as a function of time. What is the meaning of ds changing as a function of time? That is something strange. B changing, I know, I can imagine that magnetic field is changing. What is the meaning of area changing? Which means that I have to imagine that I have a coil whose size is changing. Expanding and contracting coil as a function of. So let us take an example that way. Again, I have a magnetic field in the space, and this time I am not going to say B is equal to B naught cos omega t ay, because I want my magnetic field to be constant. So I am going to say B is equal to B naught in the ay direction is my magnetic field, and my notion of xyz is, okay, let me just put this as az just to make sure that we understand how to work with all directions of x, y and z. The way you would choose your x, y, z is such that you follow the right handed notation, which means as you move from x to y, your thumb should move to z. In electromagnetics, please don't get confused with right hand rule and left hand rule and right hand screw rule and things like that. There's only one rule you need to use, which is the right hand rule, right hand cork rule, which means that when you have a vector A cross B, the direction is along the thumb. All other rules are only derivables from this right hand rule. Okay. So now in this field, I have let's say a coil whose width is L, and instead of having the coil completed this way, I have a rod, which is a conducting rod, which completes the path, and this rod is movable. Okay, so I can move this rod forward and backward. Now let's say the rod is moving velocity v0 in the direction a1. A rod is moving. So what happens as the rod is moving? The flux psi is again surface integral v dot ds. It's not a closed surface, it's an open surface, because I am trying to calculate the flux through the coil, and let's say my loop integral direction is this, clockwise, so that my ds is now an elemental area. Now the length of that elemental area is along the y direction, the width is along x direction. So this is dx dy, and the direction of the surface is to inward. Again, use the same rule as I said earlier. Point your fingers along the direction of this curling direction of the circular loop that we have marked, then dx dy, and it should be along the az direction. So my psi is v0 az dot dx dy az. Now I have to do a double integral here, because my x is along, so remember this is along my x, this is my y. So x is from 0 to L, and y, whatever was my initial position, I have to look for a time t. After the end of t, the rod has moved to this position, and the new position or this difference should be v0 t. That's a distance moved by the rod in a time t. So my y should be equal to original y, which is, let's say, y0, or I could even have, okay, so this is y0 plus v times t, v0. So this integration is going to give me v0. Integration over x is L, integration of y is v0 t, and because it's a dot product in the same direction, I get this. This is my psi. Now my Faraday's law would give me, this is only the flux. My Faraday's law tells me that loop integral E dot dl is minus d by dt of psi. So this is minus v0 L v0, because if I differentiate this with respect to time, the t goes away. So I got my induced EMF in this system. E dot dl is equal to minus b L v0. Again, how do I interpret my Lenz's law? I interpret Lenz's law by observing that this is my loop, and in a time t, the loop had tried to increase the area. Okay. In a time t, the location changed from y equal to y0 to y0 plus v0 t. So what had happened? The loop was trying to expand. Now what is the induced current doing? This is my induced current, direction of induced current. That produces a magnetic field into, as the loop was expanding, as the size of the loop was expanding, the flux was increasing. Magnetic flux through the loop was increasing. According to the Lenz's law, what should it do? The induced EMF should be such that it should reduce the flux. How can it reduce the flux? It can reduce the flux either by reducing the magnetic field or by reducing the area. Okay, because flux is magnetic field into area. But my area is already increasing, so I can't reduce the area. So what it does is, it induces the current in this direction, but you know the current is not actually induced in this clockwise direction, because you see I have a negative sign here, which means the induced current is actually in this direction. direction marked in arrow because of that negative sign. Because your velocity is increasing, the area of the loop is increasing, the induced current is in the opposite direction, which means that when the current is in the opposite direction, the magnetic field is induced in the opposite direction, which means the induced current produces a magnetic field which opposes the change. What was the change? The change is increase in flux. So, you already have a magnetic field in your direction, the induced current is producing a magnetic field in the opposite direction, so that the net magnetic field is reduced, and when the net field reduces, your flux comes down. Okay. So, this is how we understand Lenz's law here. Same way you can argue the other way around. As the rod moves to the left, the area reduces, and when the area reduces, I can represent it as a velocity going in the negative direction, and the velocity is negative, your flux is, induced EMF is positive, which means it tries to increase the velocity. So, it's very nice to actually physically understand Lenz's law through these example, because if the bar is moving to the right, the induced EMF produces a current which tries to move it back. The bar is moving to the left, it tries to move to the right. Now, the same principle is used for the working of generators, right. You will have, in a generator, instead of increasing and decreasing the size of the coil, what you do is, you will have a constant magnetic field, and in that constant magnetic field along the z direction, you would keep a coil in this plane, and then you will rotate the coil about the z axis. So, initially the field is in this direction, coil is in this direction, your ds and b are in the same direction, you have large induced field, and as the coil is rotating, the induced field reduces, becomes 0, and it keeps on rotating. So, this is the working principle of an electric generator. You would have learned this as the working principle of generator in your machines, electrical machines motors course. It is exactly the same concept. So, with that, what we can do is we can move on to the next law. So, what we did was Faraday's law, and we have written the integral form of the Faraday's law, because we have written Faraday's law as an integration. So, this is the integral form of Faraday's law. And this is the integral form of the Maxwell's equation also. Now, there is something called as differential form. We will come to the differential form, but before we come to the differential form, let us look at Ampere's law. That is the next law. Now, in Faraday's law, we talked about, Faraday's law talked about generation of electric field. We said time varying magnetic field will produce electric field. Ampere's law is going to consider the reverse. It is going to consider the generation of magnetic field. What is the cause here? Time varying magnetic field. A time varying magnetic field actually resulted in an electric field. The effect is generation of electric field. Here the cause is either steady or time varying electric field. A steady current also produces a magnetic field, time varying current also produces magnetic field, okay, and the effect is generation of magnetic field. So, that is a very nice connection between Faraday's law and Ampere's law. One law talks about how magnetic field is produced, the other law talks about how electric field is produced. And in fact, as I said, historically speaking, it was Ampere's law which we should have talked about first, because it was known, very well known in 1800s, late 1700s itself, that whenever there was a current through a conductor, you bring a compass needle next to the current carrying conductor, the needle starts deflecting, which means a current carrying conductor produces a magnetic field. But the reason I am discussing Ampere's law after Faraday's law is to just prove the point that you needed a time varying magnetic field, which means you needed a d by dt of B dot ds, right. You needed a d by dt of B dot ds to produce a loop integral E dot dl. If I apply the same parallel, a time varying electric field which is d by dt of d dot ds, this is electric flux, right, surface integral electric flux, that will produce magnetic field. This has to produce H dot dl. Okay. But a steady current also produces H dot dl. So, H dot dl should have a source, not just I, it should also have a source from d by dt surface integral d dot ds. Biot-Savart's law actually talked about generation of magnetic field from steady current. But I am going to generalize this and I say that loop integral H dot dl is actually equal to I plus d by dt of surface integral d dot ds. This is the most general form of Ampere's law. By the way, your magnetic field intensity is mu naught times H, where H is the B is a magnetic flux density, similar to D, and H is the magnetic field intensity, and we already know D is electric flux density and E is electric field intensity, and D is related to E through D is equal to epsilon naught E in free space. This is also in free space, and D is epsilon naught epsilon R E in a medium, where epsilon R is the relative permittivity of the medium. This actually tells you the response of the medium. So, this is your Ampere's law. Even though it looks little complicated, actually it is not. This actually tells you how much is the magnetic field produced. If you understand Faraday's law, you know that similar to electromagnetic EMF, electromagnetic force, this you can think of a magnetomotive force. And what does the right hand side say? The first cause of magnetic field is steady current. So, this is the first Oersted observation. The current carrying conductor produces a magnetic field. That is the first term. The second term comes from the parallel, that if time change of magnetic field is producing an electric current, simply means that time change of electric flux produces magnetic. D by dt of d dot ds has to produce a magnetic. Now, if everything is static, when you say static, it means that no time variation, which means that d by dt is 0, in which case the Ampere's law reads as H dot dl is equal to I, current. You can write it as B dot dl, because B is equal to mu H, so H is B by mu, so this is mu naught I in free space. What about Faraday's law? In static case, I have everything static, so E dot dl must be equal to 0 because there is no time variation. Now, you might want to ask this question, current is the flow of charge, rate of flow of charge. So, when you talk about static case, will I have current or will I not have current? Everything should be stationary, isn't it, for a static case? Well, static case does not mean that, it simply means that the fields do not change with time. Current is in steady state the rate of flow of charge. Okay. So, this I in static case is the steady current. It is like saying if I have a battery and I have a resistor and I have a current, this is steady current. You do not say that the battery is, you do not say that the current is flow of charge, so it is dynamic. No, we are talking about steady current like from that of a source of a battery. And if there is a steady current through a coil, which means I have a coil, which means even this conductor, as it is taking the current, what this law tells you is that it induces a magnetic field, and that magnetic field is given by this. So, let us try and find out what is the magnetic field due to a steady current. So, let us say I have a current carrying conductor, it is carrying a current I. I know from my high school that it produces a magnetic field around it, right? Magnetic field is around it, B or H. Now, I want to calculate that, how much is the magnetic field. So, the way to do that is using this loop integral H dot dl is equal to I, the current enclosed. Now, the objective is to find the magnetic field at a distance r from an infinitely long conductor. Means that because the problem has cylindrical symmetry, I am going to use cylindrical coordinate. But still the site is okay. Is audio audible? Can you tell me from which point should I repeat, because I don't know when you lost my audio. Can somebody type out from which point should I start repeating? Okay, cylinder formation. So, we are trying to work it out in the cylindrical coordinate system because the problem has cylindrical symmetry. So actually this turning off this mic is prompting me to suggest to you something, that we are so much dependent on DC power that we should think of harvesting, energy harvesting from the DC. We talked about all these antennas giving rise to electric and magnetic fields, right? You have the cell phone towers around you. It's continuously throwing electromagnetic energy at you. And you're using only a part of the energy only when you want to receive your call. But all that energy is available around you. Okay? It's just radiated, free. So what you should think of is some energy harvesting technology, way of inducing that EMF. You keep the coil in the right direction. Your good old Faraday's law will help you to induce EMF from all the stray sources of electromagnetic energy, and then you should be able to use that for small applications like generating 2 volts for running this microphone antenna. Okay. There are lots of research work going on energy harvesting, from electromechanical to DC, from using simple Faraday's law, inducing at a distance, creating, especially in toll booths, vehicles are moving on the speed breaker. There is an electromechanical motion anyway. Can you convert that electromechanical motion to induce EMF at some coil which is kept in the toll booth, which can light the toll booth? Okay. So that's a little bit of straying from what we were supposed to do. Yeah. So coming back, so this is the cylindrical coordinate system I'm trying to draw for this current carrying conductor. So the red line that I'm drawing is the direction of AR. The green line that I'm going to draw is going to be the direction of A phi. Essentially, A phi is the direction of the, so that's my A phi. So essentially my magnetic field is in the phi direction. And of course, AZ is along the Z direction. So H will have a R dependence because its strength is going to change as a function of position, and its direction is along the A phi. Okay. What about DL? So in the cylindrical coordinate system, if I look at the cross section, this is my DL, this is my DL, elemental length, this is my R, and this angle is my D phi. Or if I actually draw it a little more carefully, okay, and I have to go along this loop. So from the center, this is my DL, and this angle is my D phi, and this radius is my R. Okay. So from from the geometry in the figure, I know that vector DL, which is along the edge here, that is nothing but this angle is equal to arc into radius kind, and DL is along the A phi because it's along the edge. So that's your, so loop integral H dot DL would mean H as a function of R in the A phi direction dot R D phi along the A phi direction. Now your variable is phi, and that phi can go, that phi is this angle. So that phi is this angle from this. So that you can go from all the way from 0 to 2 pi, which means your phi is changing from 0 to 2 pi. So your variable of integration is that. So this is closed loop integral H dot DL. You are doing justice to this closed loop integral by taking phi from 0 to 2 pi because you are covering the entire loop. So this is HR, R is outside, d phi when you integrate is phi, a phi dot a phi is 1 and phi with the limits from 0 to 2 pi is 2 pi. This is the left hand side, integral h dot dl. And the right hand side is I, the current enclosed. Now the current enclosed is I've represented with small letter I in this case. So my HR is I divided by 2 pi r, and my total H is I divided by 2 pi r, which is magnitude of this in the AR direction, sorry, A phi direction. So if I were to plot H as a function of r, at r equal to 0, which means at the center of the cylinder, it's actually when r equal to 0, magnetic field is infinity. So I really can't define it at r equal to 0, but then as r increases, it goes as 1 over r. The magnetic field actually becomes 0 only when r equal to infinity. So you have a variation, right? This is h of r, which is equal to I by 2 pi r. That's a strength, which means that if this is my current carrying conductor, if I look at the magnetic field here at this specific location, it's pointing in this direction. If I look at this specific location, it is pointing in this direction, and so on. And the magnetic field here, when I compare with the magnetic field here, as I get closer and closer to the conductor, the magnetic field is going to increase. This is closer and closer to the conductor. So this is R equal to. So this is a simple way I can work out Ampere's law. Now this is again for a steady current. Now I have an interpretation of Ampere's law to make, because what we are interested in this part of this, because you would have learned Ampere's law in your high school. Another interpretation you want to make is Ampere's law for a closed surface. Okay, there are some interesting applications to this, which is why we are doing this. Let's say I have a potato, a closed surface, which is like a surface of a potato. I put a rubber band around the potato, and let's say I am cutting at the rubber band, which means I have my half potato, and let's say I want to apply Ampere's law here. Okay, so this circle is the loop, the rubber band is the loop on which I am applying the Ampere's law, and obviously this potato is placed in a region where the electric field is changing. Okay, so because the electric field is changing, it's not a static case, it's a time dynamic case, and I can say that loop integral across this C1 H dot dl is equal to, I can write current as surface integral J dot ds, right, where J is the surface current density. Current per area is known, I integrate over the area, I get the current. I integrate the current density over the area, I get the current. So this is J dot ds over the surface plus my second term. My second term was d by dt surface integral d dot ds. I am calling the surface as S1 because I am looking at the left side surface, because I have the other half of my potato on which I can apply Ampere's law. Now what is the direction of ds in this case? How should I pick my direction of loop and direction of ds? In fact, I should have done that before even I mark the direction of loop. If this is my surface, surface is pointing outside, my loop should be such that as so this is the half of the potato, this is the half of the potato, right, and here is where I am applying the loop. My loop should be such that, in fact I have drawn the direction of loop incorrectly, because the direction of my loop should be such that my thumb should point towards ds. Okay. Now if I put the direction of this way, my thumb is pointing towards the right. That's not what I have as the surface integral on the left. My surface is on the left, surface normal is outside, which means my direction of the loop should be this way, so that the surface is outward. So my direction of loop should be this way. All right. Now, what about the other half of the potato? Let's pick the other half. So the other half is here. The surface normal is outward. I need an outward surface normal. So what should be my direction of my closed loop integral? It has to be this way. So I am going to write Ampere's law for the second surface, S2. This was my ds1 or ds for the first surface. This is my ds for the second surface. And so for the second surface, if I write Ampere's law, C2. So this is C1 and this is C2. H dot dl equal to S2 j dot ds plus d by dt S2 d dot ds. So I have two halves of the potato with two rubber bands. Now what I am going to do is, I am going to bring the potato halves together and join them. Okay, I am going to club these two. Now when I club these two, it is as good as I can add these two vectors, left sides and right sides. Now you see on this left side contour, it is moving this way, and on the right side contour, it is the same surface, it is just only two halves of the same surface. So it is in the opposite direction, which means the sense of rotation in the two contours have become opposite, which would mean that when I add, the left side is going to be 0, because in one contour it is a clockwise, in the other contour it is a anti-clockwise. So the effect is going to be 0. This must be equal to S1 plus S2, the total surface. Now I have to talk about the total surface. S1 plus S2 j dot ds plus d by dt S1 plus S2 d dot ds. Now this is a very important result in Ampere's law, and the result is the following. If I take a closed surface S, which is S1 plus S2, so for a closed surface, if I apply Ampere's law, it simply states that surface integral j dot ds is equal to minus d by dt of d dot ds. Okay. Now, yesterday we spent some time in trying to understand what is j dot ds. That is a flux. This is a surface integral, is the flux. So the left side is the flux due to current. What kind of current are we talking about? The current due to conduction, flow of electrons. So the flux due to conduction is the negative of the flux due to this d dot ds, electric flux density, the flux due to the electric field. Okay. So I can think of, if I have a closed surface, the net flux is 0. That is what this statement told you. The net flux is 0, which means if I had conduction current entering, I could have displacement current leaving. Where would this make sense? Let us say I take a capacitor, and let me draw this capacitor smaller, gap bigger, and I am sending current through the capacitor. Okay. As I send current, I am sending conduction current, but I know very well that the capacitor has, between the plates of the capacitor is dielectric. This is dielectric, which means it cannot conduct. It is like glass, it is an insulator. Then how is it that I am able to get current outside? How is it that, first let me put a resistor so that the circuit looks little more practically reasonable. I have current reaching up to this plate, but what accounts for the continuity of current? Because electric currents, charges, electrons cannot flow through the dielectric. Then how is it that the current is passing through the dielectric and reaching the other end when I apply AC? Of course, when I have DC, the capacitor blocks, it does not allow current to pass through. So in DC, in static case, I do not have a problem, but if I have current as a function of time, you know RC circuits, you know what is the time constant and blah blah blah. So you want to find out what is the mechanism by which this current is reaching the other end of the capacitor, and the mechanism is through Ampere's law. It says that if I take a closed surface like this is my potato now, right? If I keep my potato like this, what enters this is not through the arrows that I have shown, but through the arrow that I am going to show now in red. What entered this system is J dot ds. What is leaving the potato? Net flux is 0. So what is leaving the potato is D dot ds, because obviously there is an electric field between the two plates of the capacitor that is decided by the capacitance, epsilon, D, area and so on. And again, if I take another surface, what entered through this surface is the flux due to the electric field, rate of change of flux to the, and what left this system is J. So this right side is performing the role of current in dielectrics, and so this, because it has dimensions of current, because left side is current, so right side should be current, this is called as the displacement current. Okay. You definitely need the help of displacement current to explain how current is continuous in a dielectric medium. Otherwise, if you do not have this, we do not have the continuity of electric current in a dielectric medium. Okay. So this is the consequence of Ampere's law, and this is the consequence of Ampere's law for a closed surface. So I have defined Ampere's law for you. The way we defined is by observing that magnetic field is produced by steady current, and just because a time varying magnetic field produces electric field, we are demanding that time varying electric field should produce magnetic field. In fact, this addition, this observation was done by Maxwell, and so this term is Maxwell's contributions. Displacement current. It is called current just because it has a dimension of current. It is called displacement current simply because it has the dimension, or it is defined through the electric flux density. Okay. So now we are equipped with two laws, Faraday's law and Ampere's law. Let us move on to the third law. So you are equipped with two Maxwell's equations now. We need to talk about the third law. In fact, these two laws, your Faraday's law and Ampere's law, actually explains the formation of electromagnetic wave, because Faraday's law tells you that whenever there is a time rate of change of magnetic flux, and the magnetic flux changes with time, you have an electric field. And Ampere's law says that whenever you have steady current, or you have a time varying electric flux, that produces magnetic field. Time varying magnetic flux produces electric field. Okay. I can show you a very simple animation which demonstrates this concept. This is from radio waves and electromagnetic fields PHET simulation. So in the right side corner you can find the source PHET. Okay. Just Google PHET, you will find some nice animations and simulations to understand the concept. So what I have is a on the left side is a where you see KPHET is a flag. Now that's not a simple flag, it is allowing electrons to move, and on the right side there is a house on which there is an antenna kept. It is also having an electron, and this right side electron will start wiggling whenever it receives an electromagnetic wave. How is that electromagnetic wave received? You need to first start creating a time varying electric field or time varying magnetic field. It's easier for us to produce a time varying electric field. How do you do that? You send electric current. It is not enough that you send electric current. If I just send an electric current, what I created is a disturbance, and that's propagated. That's all. Because I just created a disturbance, which means for an instant I created an electric field. It's not continuously time varying. Let's say I wiggle it a little bit, right? So I created a time varying electric field, that created a time varying magnetic field, which in turn created a time varying electric field, which in turn created a time varying magnetic field, and that is what is propagating. But now if I oscillate it continuously, which means my electric field, you see electron is going down, field is going up, because remember field is a direction of force experienced by positive charge. So as the electron is coming down, the field is going up. And as the field is oscillating, I am continuously creating a time varying electric field. So there is a change in flux, which produces a change in magnetic flux, which further produces change in electric flux, and that's how it is propagating. Why does it propagate in space? That we will see in tomorrow's class when we do the electromagnetic, when we do the solution for the wave equation. Okay. Now this actually tells you as this current is moving, it actually tells you the direction of electric field and direction of magnetic field. So if I just say electric field, it's telling you how the electric field is varying as a function of position. Okay, Gauss law. After we finish Gauss law, we will break and I can take your questions. So Gauss law states that the displacement flux. How do I write the displacement flux? Electric displacement B dot ds. And Gauss law actually talks about displacement flux from a closed surface is equal to the charge enclosed charge contained in a volume enclosed by the surface. Okay. So if I have a closed surface like that of a coconut, if I have a closed surface like a coconut, right, the net flux that is coming out of the coconut is equal to the charge contained in the volume of the coconut, which is enclosing that surface. So if I have a volume distribution rho, if rho is the charge density, volume charge density, so that the charge is rho dV, volume integral rho dV, then Gauss's law states that the closed surface integral is equal to volume integral rho dV. Some people put it as triple integral for volume integral and double integral for surface integral and so on. But so long as you understand that it has to be surface integral and volume integral, it is fine. Now the beauty is you can derive this Gauss law from Ampere's law. Before we do that, this is Gauss law for electric field. In fact, a variation of this is what you have learned in your first class of electromagnetics. Let's say I have a charge Q. It generates an electric field all around. right? And this Gauss law tells me what is a flux due to the electric field, flux due to the charge, and that flux is d dot ds is equal to the charge. If q is a charge, the right side will get replaced by q. And I can actually use Gauss law to find out the force due to the electric field intensity due to the point charge. Because if I have, let's say, a point charge q here, I write down what is a flux in a closed surface integral. I can evaluate this integral and then I can find out how much is d as a function of. Now, in case of magnetic field, you know that the simplest realization of a magnetic field is when you have a magnet. And if I take a closed surface anywhere in the magnetic field, and if I am trying to write this integral closed integral b dot ds, that is going to be 0 because I have flux entering, leaving the system, the flux entering the system and the flux leaving the system, net flux is 0. I have as much flux entering the system as much as leaving the system. So this is b dot this is b dot ds is 0. Another way of saying it is, I can't find, just like how I can find an individual positive charge, I can't find an individual magnetic pole. So this one is your Gauss law for magnetic field, this is Gauss law for electric. Don't confuse this with Gauss divergence theorem, which was connecting the divergence of a vector, volume integral of divergence and surface integral of the vector. This is Gauss's. Associated with this is also called as the equation of continuity, which simply states that in a region where I have charges that is moving, if I have moving charges q of t or rho of t, integral of rho of t will give me q of t, and because I have moving charges, I will have current flowing out or flowing in depending on the charges that I have. Equation of continuity simply tells that it's just conservation of energy or conservation of charge. The net flux through the surface, the current through the surface must be due to the negative d by dt of charge. The flux that is coming out, current is a flow of the positive direction. So, if I talk in terms of charge, it is minus d by dt of rho dv. This is equation of continuity. Now, we talk about derivation of Gauss law. I know from Ampere's law, remember we applied Ampere's law on a potato, and the potato statement is of Ampere's law is closed integral j dot ds must be equal to closed integral d by dt of d dot ds. This works only for closed integral. Okay, but I know that from equation of continuity, j dot ds is minus d by dt of rho dv from here, which means the right hand sides must be equal, which means minus d by dt of surface integral d dot ds must be equal to minus d by dt of, or I can pull the d by dt together inside, minus volume integral rho dv must be equal to 0. Now, obviously, if the derivative of something is 0, it means that this is constant with time, this term is constant with time, which means that d dot ds minus rho dv is constant, and there is no reason for me to believe why that constant, there is no other evidence which tells me that this constant is non-zero. So, it actually means that this term is a constant, and I do not have any experimental evidence which shows that this constant is a term other than 0, which means that d dot ds is equal to rho dv. So this is my statement of Gauss law. So essentially we proved Gauss law from Ampere's law. Ampere's law, and of course we used equation of continuity. Okay. So to summarize, we have actually worked out all the 4 Maxwell's equations today. The first Maxwell's equation is Faraday's law, which talks about generation of electric field whenever there is a change in magnetic field. Ampere's law, which talks about generation of magnetic field whenever there is a current, steady current J dot ds, or a time varying current, which is time varying field. We talked about Ampere's law, which said closed surface integral d dot ds. Remember, the left sides are all closed surface integrals, right sides are not closed integrals. This should be just surface integral b dot ds. This is volume integral rho dv, and closed surface integral b dot ds equal to 0. These are the integral forms of Maxwell's equations. Now there are other forms for these equations which are called as differential forms. I think I'll break for 5-10 minutes and before continuing to the differential form of Maxwell's equations. I'll also tell you the reason why we would use integral form and why we would use differential form. Under what context do you use integral and what context do you use differential? So opening the class for discussion, please raise your hands or type in your chat window if you have any questions. What we wanted to say was, if I take a closed surface integral, a closed surface, and I am trying to apply Ampere's law on the closed surface. When I apply Ampere's law on the closed surface, Ampere's law which says that this is my Ampere's law. Okay. Now this, if I were to apply on this surface, the right sides are open surfaces, whereas the left side is a closed loop integral. As such, if I just have a big potato, I cannot apply Ampere's law because it doesn't. I need to figure out a way to apply how to apply it for a closed surface. The right side of the Ampere law is actually an open surface. It's only the line integral. The loop integral is a closed loop. So what I do is I cut this into half, okay, and in the first part I apply Ampere's law. Now the surface is outward. I want to find out the ds for that, direction of ds. Direction of ds is outward normal. The moment I have it as outward normal, then I lost my freedom to choose my direction of loop integral, because ds is the outward normal, that should go in the direction of the thumb. The loop integral should go clockwise, which means my loop integral should be this way. Okay. Now in the other half of the potato, which is like this, my loop integral has to be decided by the direction of surface normal. This is my surface normal. Okay. Now to comply with the direction of surface normal, I need to apply my loop integral direction this way, so that my thumb points to the surface normal. So that gives me this direction. What I did after that was I just wrote down what is the Ampere's law for the first half and the second half. And now I wanted to find out what is the Ampere's law for the complete surface. I know that the complete surface I can find by joining both these surfaces. That is why right hand side I simply join S1 plus S2 and form the complete surface. So I just simply added these two to form the complete surface. But when I add the left sides, you see the contour of the left hand side piece and the right side piece are in opposite direction, which means whatever is the result of this integral would be negative of that. So if I add the left side, it is going to be 0. Okay. So which is why I get a kind of continuity equation from applying Ampere's law on a closed surface. And more than the Ampere's law, the application of this Ampere's law on a closed surface is more interesting, because there was another query on what is this displacement current. So I was actually building it up to the displacement current by explaining this. So as we I'll repeat the example of the capacitor. I know that a capacitor does not conduct DC, it blocks DC. But how is it that the capacitor is able to bypass AC? It is able to pass alternating current through it. Ideally, the space between the capacitor is filled with a dielectric. So it is not supposed to allow conduction current to pass through. Then how is it that conduction current is reaching the other end of the capacitor? The answer to that is through the time varying electric field. So as I am applying an sending a current, I am applying an electric field onto the plates. And if this end is positive, this end is negative, the direction of electric field is from left to right. Now as I changes with time, my electric field also oscillates with time, because of which my D oscillates with time, because of which the flux oscillates with time, because of which I have a non-zero component for minus d by d, non-zero value of displacement current. So in the wire, current is due to the conduction current, whereas in the metal I don't have electric field, so I cannot have conduction current through the wire. Whereas in the region between the capacitors, my conduction is carried out not by the conduction current, it is carried out by the displacement current, because conduction current cannot penetrate through the dielectric. So what is happening is this flux, electric flux is changing with time, that is creating a current which we call as a displacement current, and continuity of from this Ampere's law. So you again apply the closed surface rule here. Flux entered this surface as conduction current, but it will leave the surface as displacement current. Here again in the second surface that I picked, flux is entering as displacement current, it is leaving as conduction current. So this kind of displacement current originating because of the electric field changing with time is necessary for us to explain electromagnetic wave. Okay, so I have many questions now. Let me start going one by one. So I think this is what we answered. The next question I have is RF transmitter example. Okay. So what did we say? We said that if my coil and the magnetic field, this is the direction of magnetic field towards you, my coil is perpendicular to the magnetic field, I get largest induction. But if my coil is parallel to the magnetic field, I get no induction, which means if there is a source of electromagnetic wave which is somewhere else, and I keep a coil and I find that in a specific direction I do not have induction, it means that magnetic field is parallel to that. Now I do the experiment at another height, and again I find a direction in which magnetic field is parallel, which means I do not get induction, I get the magnetic field parallel. I get two directions in which the magnetic field is parallel. I can extrapolate. So I got two directions, let us say this one and let us say this one as the two directions. it means that my line of sight, my electromagnetic field would have come. The first case, the magnetic field is in the coil is in this direction when I have 0 induced EMF. In the second case, I have like this. If I extend this lines, because my propagation of electromagnetic wave is perpendicular to the magnetic field, this must have been the position of my transmitter. So that is the RF transmitter example. Displacement current, I just repeated displacement current. How vectors D and ds have different directions. Obviously, D and ds are two different things. So they will have two different directions. The question is rather, how do I find the direction of D and ds? So ds depends on the, remember this potato example. ds is just the surface normal. So if I keep the surface normal like this, let's say it's a cut coconut. This is my surface, my ds is in this direction. If I am keeping the cut coconut this way and this is my ds, it's in this direction. So ds just tells you where your surface is. For example, I create a surface like this. Okay, I am going to roll this and create a surface. Where is ds now? ds is outward normal. If my surface is, let's say, like this, where is ds? The surface that I am considering is bent, is outward normal. What's the ds here? It's outward normal. So I will say in this case ds is along the r direction, radial direction. It's a flat sheet of paper, rectangular coordinate, flat sheet of paper. Where is ds? It is outward normal, this way, or it could be towards me. Whereas d is a direction of electric field. D is epsilon E, D is the direction of electric field. Depending on where is your electric field, your D direction is different. Magnetic field produced by conduction and convection current are same or not? Now you typically have this concept of convection current only in plasma. Okay, so in plasma, you talk about charges flowing freely, so you have the current. So you typically don't differentiate between conduction and convection just like in thermal flow. Okay, so when you say J dot ds, it actually involves conduction, convection, everything. Any source of current is J dot ds. So I think I did this again, conduction current and displacement current. So just to repeat, conduction current is because of the flow of electrons. Displacement current is due to the time rate of change of electric flux. I could have situations where I have both flow of electrons and time change of electric flux, or I could have a situation where I could have a situation where I have only change of electric flux but no flow of electrons. So if I take a capacitor with a dielectric, inside this dielectric I have displacement current because I can't have electrons flowing inside the dielectric. Whereas in a wire I have conduction current. I'll give you another example. I'm sure everybody has heard of coaxial cable. Now coaxial cable, I can probably bring a coaxial cable in the class next day. It's like your BNC cable. I hope you have heard what is your BNC cable. The cable will have a thick wire. It will have dielectric around it, white dielectric around it. and on top of that it will have another conducting layer around it. So here you have dielectric, you have conductor at the center and conductor outside, and then the whole thing will have a covering, black covering. Okay. So the way I represent coaxial cable is like this. Okay. The ones marked in red is conductor. Now, a coaxial cable works this way. When you connect to a battery. Now, I don't know, everybody would have used oscilloscopes. Yes? You have a specific kind of cable which you plug it into your oscilloscope. That is a BNC cable. That's a coaxial cable. Okay, these are cables which you use along with your oscilloscopes and signal generators. So what you will have is this gets connected to, let's say, positive. This gets connected to a load and gets connected to the negative like this. This is your signal generator, this is your oscilloscope. I could use a DC to the oscilloscope. I could connect a DC to the oscilloscope, right? So I'll get a DC value. How does the current flow through this? I have from the positive, it goes through this, goes through the oscilloscope resistance, and this is the return path. Okay. What's the direction of electric field here? This is the negative terminal, this is the positive terminal. So I should have electric field along the radius. If I look at the cross section, my electric field is along AR, radially outward. Because the center is positive, outside is negative. I'm looking at the cross section. Outside part is negative. You see the center I have connected to the center of this. Outside is negative. So my electric field is radially outward. First of all, would it have a magnetic field? Of course, it will have a magnetic field because it's a current carrying conductor. Now, what's the direction of magnetic field? The center is carrying a current here. So I will have a magnetic field around the center. So if I draw the cross section, this is the center. Let's say current is going into the wire. So what's the direction of magnetic field? My movement of fingers would show me a magnetic field direction. This is the direction of magnetic field. This is the direction of magnetic field. So this is the conductor. This is the outer conductor. Would I have magnetic field outside the outer conductor? Would I have magnetic field in this region? Would I have electric field in this region? I wouldn't, because the plus and minus are ending. Would I have magnetic field outside? I wouldn't, because if I take a loop outside, what's the net current enclosed by the loop? I have some current flowing in, I have some current flowing out, equal amount of current flowing out. So if I do integral h dot dl, your I enclosed is 0. for this loop. So I really don't have electric field or magnetic field outside the cable, coaxial cable. In fact, that's the purpose why you are using a coaxial cable. You want to confine all the electric field and magnetic field inside the cable. What happens if I don't have a coaxial cable? I just have two wires. Let's say I have a two wire. I have the source. I have the load connected like this. I have current. I have current. I have magnetic field all around, isn't it? I have the magnetic field due to this all around. I have the electric field also all around. So the reason why I have a coaxial cable is to confine electric field and magnetic field. Now the question is, what is displacement current direction in this coaxial cable? What's the direction of conduction current? Conduction current is flowing in the direction of my black arrow. What about the direction of displacement current? Now displacement current is d by dt of surface integral d dot ds. It has to depend on the field. And where is your field? Field is in the radial direction. So if this radial field is changing with time, then I have displacement current there in that region that's changing with time. So this is an example where I have conduction current and displacement current in the same place. Capacitor was an example where I could isolate, or rather I can say that even in this case, in the coaxial cable, if I exaggerate the central conductor and outer conductor, my conduction current is happening in the shaded region, wherever I am shading, because current is entering, it is due to the flow of electron. It is going through the inner conductor, coming out of the outer conductor. It is physical flow of electrons. But where is my displacement current? I am going to mark the displacement current in the as a dotted region. My displacement current is here. Because my electric field is here and displacement current is because of rate of change of electric flux density. So here is where I have my displacement current. And here is where I have my conduction current. You need both of these, especially displacement current, if you were to explain the concepts of, or you were to explain the fact that a time varying electric field will produce a magnetic field. If there was no displacement current, you wouldn't generate a magnetic field due to electric field, which means electromagnetic field generation would not have been possible. I hope I answered this question. Next one is, when we apply electric field, did the propagation of wave takes place in one direction only? So this was probably referring to the simulation we saw. When we apply an electric field, actually what I showed you is a very simplistic simulation where as I apply electric field in a specific direction, I generate electromagnetic wave in a specific direction. It's a very simplistic case. Tomorrow when we write the wave equation, I can tell you more about the direction of generation of electromagnetic wave. Okay, why will we use integral form of Maxwell's equations? So all Maxwell's equations were in their first principles defined as integral forms. Why do I use them? I use them in cases where I want to apply Maxwell's equations on surfaces or loops. So when we do, our next topic is boundary conditions. So when we do boundary conditions, we are trying to find out, in boundary conditions what we are doing is, we are trying to find out what happens to the electric field and magnetic field when you are going from one medium to another medium. Let's say this is air and this is glass, and I apply an electric field like this. And I want to know what happened to the electric field inside glass, or this could be glass, it could be metal, it could be copper, it could be anything, could be another dielectric also. So if I were to find out what happens to this electric field when it encounters a change in medium, what I will do is I will take a loop which is partly in this and partly in the other medium, or I will take a surface like this which is partly in this and partly in the other, and then I start applying my integral form. Okay. So this tells me how the electric field behaves in different media. But as I said, there is something called as a point form also. Let us say I want to find out the electric field at a specific position in a homogeneous medium. Integral form is not going to help you, point form will help. So tomorrow we start with point form, and then we can move on to the boundary conditions. Why do we use Ampere's law to derive Gauss law? Well, Ampere's law, Gauss law gave me Ampere's law, so I use Ampere's law to derive Gauss law. Essentially, it's not that originally Gauss law got derived from Ampere's law or anything like that. It is just to, the reason I showed I derived Ampere's Gauss law from Ampere's law is to show that these are all self-consistent with each other. All these four equations are self, you can derive one from the other. It is just to show that. It is not that for the first time in the history Gauss law was derived from Ampere's law. Need clarity of RF transmitter diagram. I probably can come back on that. I just wanted to know what is the clarity you need. Okay, the next one is a field works on toroidal and solenoidal coil. So this we will work as a tutorial problem. There is a tutorial problem on solenoid and toroidal coil. So tomorrow's tutorial problem I can work it out. Does the Faraday law work under the assumption if no current flows through the solenoid? Well, what is the Faraday's no current? Faraday's law talks about induction of current. So I really don't understand this question when you say I am assuming that no current flows through the solenoid. Actually, Faraday's law says that whenever I have a change in flux, I have field induced. So I probably cannot work under the assumption that no current flows through the solenoid. This is a question from which says that in Ampere law, how can we assume that the sum of current density and electric phase density is 0? What probably they mean is, how can I assume that sum of current density, it is not sum of current density and there is no electric phase density. Sorry, I think you have understood it completely wrong. What we proved is that the sum of, this is not current density. The first term is flux due to electric current. This one is the flux due to displacement current. And what we are, I am not assuming anything here. I am proving, I am actually proving that the sum of electric flux and flux due to electric conduction current and the flux due to displacement current is 0. I think you people got it, did not get it completely. Next question is it possible to find the direction of EMF directly Faraday law without invoking Lenz's law? No, it is not possible. Faraday's law has to be worked with Lenz's law only. I can just repeat what I said earlier. What I do is I find the coil direction for which I have 0 EMF. Let's say this is the coil direction for which I have 0 EMF. It means that magnetic field is in this direction. Magnetic field is in this direction. Direction of propagation of the electromagnetic wave is like this. Now I keep the coil at a vertically separated position, and let's say I got this as my direction of coil for which 0 EMF, which means that my magnetic field is in this direction, and because magnetic field is in this direction, my electromagnetic wave should have been like this, which means the wave should have come from this source. The first coil is telling me the direction. The second coil is helping me to find the exact location of the source. So I hope that answered your question. Okay, if there are no more questions, what we can do is